Hello everyone, welcome back to this channel. In this video, we are going to look at the problem called aggressive cows from Sphere Online Judge platform. This problem is quite old, as you can see, and it's very interesting as well. You can go through this problem statement here, but I'll try to summarize the problem in simple words. So basically, we'll be given n number of stalls along with c number of cows, and we'll be having positions of n stalls. Okay, our task is to place C cows in the stalls such that the minimum distance between any two cows is maximized. Okay, we have to place them in such a way that the minimum distance between any two cows is maximized. So in this example, these are the positions of n stalls. So let me first write the positions in ascending order. So the first stall is at position 0, then next stall is at position 3, then next stall is at position 4, then 7, 9, and then 10. So these are the positions of 6 stalls, fine, and we need to place 4 cows. So let's just consider that we place the 4 cows in this way. So we place all the 4 cows in stalls. Okay, so after placing these 4 cows, if we place them like this, what is the minimum distance between any two cows? So, as you can see, the minimum distance between these two cows is 3, and the minimum distance between these two cows is 1, and the minimum distance between these two cows is again 3. In this case, the minimum distance becomes 1 between any two cows. Let's consider a different solution. If I place the first cow at this position, okay, then the next cow at the second stall at position 3, fine. Then the third cow I place it at this stall at position 7, and the fourth cow I place it at this position. Now in this case, the distance between these two cows is again 3 only. Then the distance between these two cows, 7 and 3, so it will be 4, and the distance between these two cows will be 3 again. If we place the cows in these stalls, then the minimum distance between any two cows will be 3. And since 3 is greater than 1, we need to maximize the minimum distance, so we are going to consider 3. Okay. Now, since we are concerned with the minimum distance between any two cows, it means that it's always better to consider just the adjacent stalls only, right? Because there is no point in comparing non-adjacent stalls because uh, if I consider these two stalls, then they are not adjacent to each other. So the distance between these two will be greater. But we are concerned with just the minimum distance between any two cows. So just finding the distance between the adjacent stalls will work for us. Okay. And also, whatever is the input array, we'll first sort it in ascending order. Okay. Because we want the positions of stalls in ascending order. And then we need to find the maximum minimum distance between any two cows. I think by now it is little clear what I mean to say. Whatever is the minimum distance between any two cows, we want it to be maximized. So, and we need to find that. Okay, what is the first approach that we can use? Whatever is the minimum possible distance, so the minimum possible distance is 1, right? So I start from 1 and I try to accommodate my cows. So if there are 4 cows, I try to position them in these stalls such that the minimum distance between the cows is at least 1. So if I am able to place my 4 cows such that the minimum distance between them, between any 2 cows, is 1, then it means that 1 can be a possible solution, right? Then I'll increment the value to 2. Now I'll try to position my cows such that the minimum distance between any 2 cows is at least 2. Okay, such that the minimum distance between any 2 cows is 2. So like this, I'll check all the valid configurations. If distance of 2 is also valid minimum distance, then I'll move to 3. Then I'll check for 3. I'll keep updating the value. Now I'll check for 4 and 5. The moment I am not able to accommodate my cows, let's say for value 4, I am not able to place my 4 cows such that the minimum distance is at least 4. I'll stop because if I'm not able to maintain the minimum distance 4, then I'll not be able to maintain distance of 5 as well. So I'll stop and my answer will be 3. So the maximum minimum distance was 3, so I will print 3. Before we move to the optimal approach, let us first see how are we going to check if a distance is valid or not. Let me take the positions of stalls. So these are the positions of stalls. Let us consider a distance of 1. We'll check if we can place our 4 cows such that the minimum distance between 2 cows is 1. So the thing is, it's always better to start from the first stall because if instead of this stall, if I place my first cow at this position, at this stall, and then the second cow I place at this stall, then I don't have any other choice. I still have 2 cows to place, but I don't have any more stalls left. So that's why it's always better to start placing cows from the first stall itself. Now after this, I need to check for distance 1. After placing my 4 cows, can the minimum distance be 1 or not? So if I place my first cow here, second cow here, then the distance between these two will be 3, not a problem. Now I'll place my next cow at this position. Here the distance between adjacent cow at position 3 and 4 becomes 1. And then I'll place my fourth cow at this stall at position 7. So here also the distance is 3. So as you can see, the minimum distance between any 2 cows is this one. It means that we were able to maintain minimum distance 1. Hence 1 can be a valid solution. Now let's check for other values. So if I want to check for some other value, I'll follow the same approach. I'll start placing my cows by placing the first cow in the first stall itself. So now I have checked for distance 1. Now I'll try to accommodate my cows such that the minimum distance between any 2 cows is 2. Okay, now I need to check this whether I am able to place my cows with minimum distance 2 or not. So I'll place my first cow at this stall. Then I'll place my second cow at this position. So the distance between them is 3. Then I'll check if I place my third cow at this position, then the distance between the adjacent cows becomes 1, right? But we want the minimum distance of 2. So it means that we cannot place the third cow at this place, so we'll leave this stall. Now I'll try to place my third cow at this stall. So if I place it here, then the minimum distance between adjacent stalls becomes 4, right? So here the minimum distance is 4, so it's not a problem. Now I need to place my fourth cow. If I place my fourth cow here, let me change the color. If I place my fourth cow here, then the distance between the adjacent cows becomes 2. 2 is the minimum distance in this configuration. This means that 2 is a valid solution. We can attain minimum distance 2. Similarly, I'll increment it to 3 and I'll check if I can accommodate my cow such that the minimum distance is 3 or not, and so on, unless I am not able to accommodate my cows. And then whatever is the maximum minimum distance, I will print that. Okay, so this was the first approach. We linearly check for all the minimum distances, and whichever is the maximum, we print that. So we have seen the first approach where we will linearly iterate through all the possible values of distances, and the moment we are unable to accommodate or place our cows such that the minimum distance between them is that value, we will stop and we will simply print whatever is the maximum value we can attain. So for linearly checking, for linearly checking the minimum distance, we can start from 1 until when we should continue. So what can be the maximum distance between any two cows? So the maximum distance will be when I place my one cow in the first stall and the second cow I place my first cow in the first stall and the second cow in the last stall, then the distance between them is the maximum possible distance that we can get, right? So in this case, the maximum possible distance is 10. So in our linear search also, we will continue checking for minimum distance till max minus min positions of stalls. Okay, and we will keep checking. Inside the for loop, we will write something like this. So if I am able to place, if the distance I is a valid minimum distance, if I'm able to maintain minimum distance I between my cows, then it means it's a valid solution. So if I is a valid minimum distance, to the is valid function, I'll also pass few other things like the array given to us. So if the array name is distance, I'll pass it along with the number of cows. So number of cows given to us was C, but I'll simply write cows for better understanding. So if I is valid, then I'll update my answer to I. If it is not valid, if I'm not able to get a minimum distance I, then it means that I need to break out of this loop, because if I'm not able to place, let's say if I'm not able to maintain a distance of 4, then it obviously I'll not be able to maintain a distance of 5 as well. So I'll break out of my loop. And in the end, whatever is my answer, which is the maximum minimum distance between any two cows, I will print that. We have already discussed how we are going to check if a distance is valid or not. So we will write that function separately. So what will be the time complexity of this linear approach? So if you see carefully, then this for loop is running till max position minus min position of this stall. So it means that big O of max position minus min position. And along with this, we are also having a function is valid. So in this function, we are checking if we are able to get minimum distance I or not. So this function time complexity will be big O of n, where we are having n number of stalls. So time complexity of the entire approach becomes okay. So this is our time complexity, and space complexity remains constant. So can we solve this in better time complexity? We have seen a solution with quadratic time complexity, right? But can we do better? If I write all the possible distances starting from distance 1, so we have 1, 2, 3, and maximum distance possible is when we place first cow here and the second cow here, right? So the distance is maximum distance becomes 10. Let me write all the values till 10. If I take a low pointer at the minimum distance, lowest distance, and if I take a high pointer at the highest possible distance, okay, then can I use binary search here? How is it going to help us? Let us see. If I find the mid, then 10 plus 1 by 2 gives us 5. So this is the mid. So 5 is a distance, right? What I'll do is I'll simply pass this 5 value to my isValid function along with the distance array and the number of cows given to us. Okay, and I'll check if I'm able to place the cows such that the minimum distance between them is 5, then it means that 5 is a valid answer. And if I'm able to place my cows with minimum distance of 5, then I want to maximize the minimum distance, right? Then I should try for the greater values, right? Since I want to maximize the minimum distance. So what I will do is I will update my low pointer to mid plus 1. Okay, so I have taken 5 into account. Okay, so probably I'll take some variable answer and I will update that answer to value 5. 5 is a valid solution, but I am not completely sure because I need to check the greater values. So I have updated my low pointer to mid plus 1, and then I will again find mid in the right half, and so on. I will continue my binary search. But if my mid was here, right? But if 5 on passing 5 to our isValid function, it returns false. So if 5 is not the valid minimum distance, I am not able to place my cows. So in this case, what I will do is I was not able to get minimum distance 5, then it means that I'll not be able to get minimum distance of 6 as well, 7 also, and 8 also. They all will fail. These values will fail, and I'll not be able to place my cows with these minimum distances. Okay, so this means that I should try for the lower values. Hence, I will reduce my search space by updating my high pointer to mid minus 1. And it's quite simple to understand now because 5 didn't work for us, so the greater values will also not work for us. Hence, I've reduced my search space to the left half. Now, again, I will find the mid value. Let's say, so mid comes out to be 2. Now, I'll pass 2 to my isValid function and I will check if I can place my cows such that the minimum distance between the two cows is 2. If I'm able to do so, then I will return true. It means that 2 is a valid minimum distance. Now, since I want to maximize my minimum distance, I will check for greater values. So values greater than 2. Within this part only, we were in this part now. If 2 is a valid minimum distance, then I'll try to maximize. I want to maximize the minimum distance. So now I'll search in the right half. So I'll update my low pointer to mid plus 1 and I will store 2 in a variable because 2 is a valid solution. Again, I will find mid value. If low is at 3 and high is at 4, so mid will be 3 here. Now again I will check if 3 is a valid minimum distance or not. If I'm able to place my cows such that the minimum distance is 3, if that's possible, then I'll update my answer to 3 because 3 is greater than 2, right? And then again I'll update my low pointer to mid plus 1 because I want to search in the right half of the values. So using binary search also we are able to get our objective, which is to find the maximum minimum distance between the two cows. Okay, but this approach is better than the previous one because here the time complexity will be better. So it will be big O of log n times n because time complexity of binary search is log n only times n because it's the time complexity taken by the isValid function, or we can say that big O of max position minus min stall position times big O of n because of the isValid function. So this is the time complexity of this approach, and it's better. This is the approach you are supposed to submit to get the accepted verdict. Okay, now without further ado, let's see the code of this approach. I have written the code in Java. So this is the main method, and here we are taking the input. We'll be submitting this problem in uh, SPOJ platform. So here we'll be given t test cases. Within each test case, we are inputting n and c. N is the number of stalls, and c is the number of cows that we need to place. Next, we'll be given the positions of the n stalls in each line. So here we are inputting those positions in an array. After taking the input, I am sorting the array. So the name of the array I have taken is A. You can name it anything. So I have sorted the positions of stalls in ascending order. So after that, I'm starting my binary search. So here I have taken high pointer, low pointer, and an answer variable, which we will keep updating if our mid value is valid. Okay, here I have initialized my high pointer to a very high number, but we can also initialize it to maximum position of stall minus minimum position of stall. Okay, since we are using binary search here, so it's not a problem because half of the array will be removed from our search space. Now here I'm starting my binary search while low is less than equal to high, so we'll find the mid value. After that, I'll pass that mid value to my isValid function along with the positions array A and C, which is the number of cows that we need to place. Okay, if this function returns true, it means that we were able to place our C cows such that the minimum distance between the cows was equals to mid. So mid is a valid solution. That's why I'm updating my answer equals to mid, and now I need to maximize my minimum distance. So that's why I'm updating my low pointer to mid plus 1. So now I will search in the right half of the integers, whatever the possible distance values we are having, we will search in the right half of it. If isValid function returns false, it means that mid is not a valid solution. We were not able to get, we were not able to place our C cows with minimum distance equals to mid. That's why we are updating our high pointer because if I am not able to place my C cows with minimum distance equals to mid, then I'll not be able to place my C cows with distance greater than mid as well. Okay, so we need to discard all the greater values as well. That's why we are reducing our search space to the left half of the integers. For that, we need to do high equals to mid minus 1. And we'll keep doing this unless we are left with just one value. And in the end, I'm printing the answer, whatever my answer holds, and t minus minus because we are having t test cases. Now let us see this is valid function also. So this is my is valid function. We are passing the mid value to check if mid is a valid minimum distance or not, along with array A and integer C, which is the number of cows that we need to place. So here I have initialized my count variable, which is the count of cows which we have already placed. And I have initialized it to 1 because we are starting by placing the first cow in the first stall. So whatever is the position of the first stall, we will place our first cow there. So basically we have placed one cow, we are left with C minus 1 cows. And since the first stall is already having a cow, so we need to start from the second stall. So that's why we are starting from I equals to 1 till the length of the array A or the distance array. Within this for loop, in this if condition, uh, here we are checking that A of I minus previous. So previous is holding the location or the position of the previous stall where we have kept our last cow. So in the beginning, it's the position of the first stall. So we are checking if the difference between the current stall position and the previous stall position, if that difference is greater than equal to mid, it means that it's okay and we can continue because we want to maintain a minimum distance of mid. Hence, I'm incrementing my count because it means that I will place my other cow in the current stall and I'm updating my previous variable to the position of the current stall, which is A of I. If if this distance is less than mid, then it means that I'm not able to place my cow in the current stall because the distance is less than mid and I want to maintain the minimum distance of mid, right? And moving on, here we are checking. So if the count, which is the number of cows which we have placed, becomes greater than equal to C, we are going to return true because our job is done, which was to place C cows. If we are done with this for loop and our count is still not equals to C, we are returning false, which means that the mid value is not a valid minimum distance and we need to check for the lower values. So that's all. If I submit this code, let's submit this also. So before submitting, I need to change the class name from aggressive cows to main. And if I submit this, so as you can see, it got accepted. If you are new to this channel, please consider subscribing and also share it with your friends and juniors. Thank you.